Yeah, now is the streaming.
Cool. Oh, so it's the same link as before, right?
I hope so. Could you
Okay.
put in the
Yeah,
chat?
I
Yeah.
can see. I can see myself. Yeah.
Mm.
All right. And copy streaming link. Oh boy, I hear myself. Okay. Um, so I'm sending email to everybody. Okay. And so for the packages, what should I say, Meena? You will announce it,
Yeah,
right?
yeah, yeah.
Okay. Okay. So I will start letting attendees in. Okay. And I'll be right back. Good morning, everybody. So we're just waiting still for a few more people to join us. We will start in a couple of minutes. Well, good morning, everybody. We will go ahead and get started little by little. So thank you for joining us again today. So I hope that the discussions from the last week were useful, and we can now continue today and tomorrow. And so somebody's asking right now about the links. So if you can see on the screen here, these are the links that we have. These links are also sent to you by email just a couple of minutes ago, together with the link to YouTube, where we broadcast this video at the same time. And I see Meena is also posting the Dropbox and the GitHub links in the chat box for you. So some of the links have been updated, in particular the GitHub. So the GitHub and Dropbox, it's the same material, so you don't need necessarily both of them. So GitHub, also Ryan posted some messages about how you can use the RStudio Cloud after the end of the course. If you want to continue practice, you should be able to continue using it in a free version, which has just a little bit less memory. There was also a question about the use of R outside of RStudio Cloud if you want to use it on your own computer. Meena will announce a little bit later the type of packages that you would need to install for today and for tomorrow's discussion as well. So today we will, and tomorrow we'll talk more about the type of analysis which are valuable for the analysis of proteomic data, and in particular for quantitative proteomic data. And today we will work with basic statistics, because one of the real advantages of working with R is that beyond just data visualization, we can also do statistical analysis, which can be very basic or maybe not so basic. And today we will just work through basic statistics and do examples of how to do this in R. And then tomorrow we'll talk about more advanced packages which you can use specifically for mass spectrometry-based experiments. Now, this said, if last weekend you felt like the discussion was going too fast and you did not keep up and you don't really know even where to start, or you're really not quite sure about the materials of last week's 2 days, my suggestion to you is to not continue with the discussion today, but instead go straight to your teaching assistants and work through the examples that we had in the last 2 days. And this is because the uh, presentation today and tomorrow it will be recorded. You can very well review it. However, the teaching assistants are already available. And if you would like to have more clarifications about what was done and just, how to start, how to do some really initial steps, do spend time with your TAs. They will be able to set you up so that later you can catch up just based on the recording. So I very much encourage you to do that. And by the way, I encourage you to ask questions, your TA's questions, which maybe go beyond what we just discussed. So do make good use of their time. On the other hand, if you feel like it was just fine and you're ready to go for the next things, then we can stay here. And so the plan for today is, as I mentioned, work with some basic statistical analysis in R, which will be led by Meena. But before we do that, I think it is really important to be on the same page about what exactly we're trying to do when we do some basic statistics. And so the plan is that the first 30 minutes, I will do a crash course on experimental design and analysis of proteomic experiments. And I really want to start with a disclaimer that this really is a crash course. So I do not want to give an impression, by no means, that if you know this, you know everything there is to know about statistics and the use of statistics in proteomics. This is absolutely not true. So the goal today, because we don't have that much time, I will just walk you through the really basic principles, which will help you kind of see what exactly we're trying to do when we start to implement these things in R. So this is really all we can hope for in this limited time frame, but I hope that it will be useful. And so I will just talk about some really key aspects of fundamental principles of experimental design, basics of statistical inference, and adjustment for multiple testing, because those come up a lot as well. And we will be using this today, but also tomorrow. Again, if you feel like you need to catch up on basics of R, don't hesitate to sign off and go to your TA, because this will be recorded and you will be able to watch it just at the end of the 3 hours today. Okay, so let's go ahead and begin. So let's see, here we go. So the first thing that I would like to tell you is what happens in the mind of a statistician when we talk about proteomic experiments. And again, I will focus only on quantitative experiments where we're interested in things such as which proteins change in abundance between conditions. And so just for the sake of the discussion, let's imagine that we have some kind of study with human samples, and we're interested in the study of disease, and we would like to know which proteins are regulated by the particular disease condition. And so in the mind of a statistician, what we imagine right away is that there are two populations out there, populations of individuals which have comparable characteristics such as age, gender, risk factors, maybe lifestyle, and so on, except for the fact that one population is healthy and the other population has the disease. But they're otherwise comparable to each other, and they are, for all practical purposes, infinite. So they're too large to actually measure every single person from this population. So if we want to study this population, so the first thing we would do is to collect a random sample of individuals from these populations. And so these are our biological replicates, which we include in the study. And this is our first layer of variation, because if we were to repeat this experiment later, we would have some other individuals. We would have the same disease, but we would have some other subjects that we include. But this is still not the whole story, because even if we can include these subjects in the study, we still do not know what are the abundances of proteins in these subjects. So we still need to go and use some assays, such as mass spectrometry assay, to measure the abundance of these proteins in the subjects. And for the moment, our measurement technologies themselves, they have all kinds of challenges. They have all kinds of uncertainty and variation associated with them. So what we actually measure is subject to yet another layer of variation, which is a technological variation. And so the goal of statistical inference, and this is really what is the kind of main thing that we're trying to do, is to look at what we observe, what we actually measure, and make some conclusions about what is not observed, about the actual populations, right? So statistical inference is take what we can see, take what we measure, and make conclusions about what we do not know, but we're interested in. And so the dangers of this process, or the danger of statistical inference, is twofold. It's bias and inefficiency. Bias means that what we measure here is systematically different from what we actually are interested in. And so bias is really bad because bias is reproducible. If we make the same mistakes, again, for example, if all our healthy subjects are female and all our disease subjects are male, then we would see some differences, but they're not necessarily due to the disease. They're also due to how we selected the subjects. And so bias is reproducible, but we can be reproducibly wrong. So the first objective of experimental design is to avoid that. And the other objective is eliminate inefficiency, meaning that our data are so noisy and have so much variance that we cannot say anything useful about what actually happens in the populations. And just very briefly, so that you have the language and be able to talk to statisticians about these issues. So usually the unknowns, so things which we do not observe, we use Greek letters for that. So this healthy population has some mean abundance of the protein, and the disease population has some other mean abundance of the protein which are not observed. The individual subjects have their protein abundances, which are also not observed. What is observed is the intensities of peaks in the mass spectra. And so for the observed quantities, we usually use Latin letters. It is a general convention in statistics. And so then the bias means that this summary of what we observe is systematically deviates from the differences in the population. And inefficiency means that the variance associated with that is very large. So this will be helpful to us. Okay, and so now, because this is what we want to do, right? We want to study what happens in the populations. Well, now we can talk about three fundamental principles of experimental design, which are replication, randomization, and blocking. So replication, I hope I don't need to convince you that we need to have replicates. So let's say we have some very simple experiment, label-free LCMS. We have only one peptide per protein. So we have some healthy subjects, we have some disease subjects. If we have one healthy subject and one disease subject, and we measure this difference, by the way, I always talk about differences, but because we think of these measurements on the log scale. And so so the difference of log intensities is the log ratio. So if you're more comfortable thinking in terms of ratios, just think of the log of the ratio. So this will become the difference of the log intensities. And the reason why we take logs is because what I will talk about in a minute, the assumptions in these methods are more appropriate on the log scale rather than on the original scale. So we want to look at the differences between these two subjects. Well, is a difference an artifact of random variation or a systematic change? And the answer is we don't know, because it can be anything. So for example, here, if we had multiple replicates and they're very tightly kind of grouped around the mean of each group, then we know it's likely to be a systematic change. But exactly the same change associated with a large variation between the subjects is more likely to be an artifact. And so this difference, right, so remember we just talked about log-fold change, may or may not be systematic depending on the associated variation, right? And so therefore, replicates allow us to characterize the variation associated with that. And because we have two types of randomness, biological variation and technical variation, there are two types of replicates, right? Biological replicates and technical replicates. And let me give you just the bottom line. Biological replicates are a lot more important than technical replicates, because if we measure one subject with many LCMS runs and we measure the subject really, really well, we still have one subject. And we don't know what is the biological variation in these populations. So this is one aspect, right? And the other aspect is that fold change cutoff alone makes no sense whatsoever, right? Because the same fold change may or may not be an artifact. So I hope I don't need to convince you that we need to have replicates. Of course, the very common question is how many replicates I need. So unfortunately, I don't have the time to answer this question, but I guess the short answer is more than people usually do, right? So the typical proteomic experiments are, unfortunately, usually have too few replicates given the objectives of the studies. If you want to know more, so I would like to direct you to our YouTube channel and also to the program, which we call May Institute, where we go into the statistical issues in a much greater detail. So I will talk about this at the end. Okay, so the second principle of experimental design is randomization. So imagine again, we have this experiment and we collected all the measurements on the healthy subjects on the first 2 days of the study and all the measurements of the disease subjects on the last 2 days of the study. So now we do see a difference, which probably is not an artifact. However, this difference can now be due to two things. It can be due to the disease, but it can also be due to the day of data collection. And our experience indicates that the latter is much more likely than the former. And so randomization allows us, and so this creates a bias, right? So this creates this systematic difference between conditions. And so a solution for that is randomization, where instead of systematically assigning all the healthy on the first 2 days and all the disease on the second 2 days, we will randomly select which subject is measured on which day. So completely randomized. And so now we see that the variability associated with this measurement is higher because in addition to biological variation, we have a day-to-day variation associated with that. However, we do not have the bias, right? So this is a much better way to do this. And again, because we have two types of randomness, biological and technical, we have two types of randomization. We need to randomize how subjects are included in the study, and we also need to randomize how all the steps of sample handling and data acquisition are performed. And so one of the reasons why I'm talking about this now is that a use of R, a very common and very effective use of R, is actually perform this type of randomization, because you really don't want to randomize, you know, just by shuffling things by hand. Humans are terrible at randomization. So you really want to do it on a computer. And so Meena will talk about how to do randomization in R. So the third fundamental principle of experimental design is blocking. And I would like to argue that this is the most effective concept in experimental design, but it is a concept that requires most statistical expertise. And I will just very briefly describe that. So as we said, if we start randomizing our samples across multiple days, our variability became inflated because now we have the biological variation compounded with the day-to-day variation. If we know that we have a day-to-day variation, we can just not control it for some reason, we can have a different strategy. We can say, okay, on day one, let me measure one healthy subject and one disease subject. On day two, let me also measure one disease and one healthy. Now, which health and which disease, I select randomly. Which goes first, I select randomly. But I impose a constraint on randomization that I have the same number of healthy and disease on day one. Then I can have the same number of healthy and disease on day two, day three, and day four. And so what I see now is that within each day, the differences between healthy and disease always points to the same direction. So in this example, the disease is always higher than healthy. And so instead of comparing the mean of healthy to the mean of disease, I can look at the differences and I can ask a question, are these differences systematically pointing in one direction? And so by doing this, we essentially can eliminate both bias and inefficiency. We'll eliminate bias because we'll make sure we have the same number of healthy and disease on each day. And we eliminate inefficiency because we essentially, by the method of the analysis, we can eliminate the day-to-day variation from consideration. And so in this example, day just has two samples. Of course, we can measure more than 2 days, in which case we need more complicated analysis methods than just the difference. And again, Meena will show you how to do this type of block randomization in R. Certain things can be done fairly easily. Other things would require statistical expertise when blocking becomes fairly complicated. And again, because we have two levels of randomness, we can block biological replicates by their characteristics such as age or gender or smoking, you know, whatever lifestyle, and also technical replicates, so which samples get processed together or acquired together. So this is really a very important part of that. And so the reason why, again, I'm talking about this, because Meena will discuss how to do this type of randomization in R. Now, the second part, I would like to make sure that we are on the same page as far as statistical inference. And I will use a very simple example of t-test, p-values, and error bars. If you have seen this before and you're comfortable with that, well, you can take it up. But I think it is really important that we are on the same page, because our exercises will be doing this type of thing. So it's really important that we understand what is actually being done. So let's look again at this simple example where we have a label-free experiment, one protein and one feature per protein. And so now we have n per subject. So now I have some number of healthy subjects with this log abundance of the feature, and some disease subjects with some log abundance of this feature. And so remember, if I go back to our mental model here, right? So I want to ask a question whether the mean in the population between these two conditions is the same, but I only observe the values of the peak intensities. And so we do not know, and we will never know what the true values are, but we can make some hypothesis. We can say, okay, let's assume, for example, that they are the same. And then the alternative hypothesis would be that they're different. So now the question becomes, what is an effective summary of our data so that we can make some kind of statements about this hypothesis? And it turns out that an effective summary here will be something which you can think of as a signal to noise, where we look at what we observe in terms of difference of the group means. So this is our signal, and the associated variability, which you can think of as noise. And so in statistical language, it's called a summary statistic. So just a summary of our data. So our signal, I think it's pretty straightforward here, right? So again, on the log scale, we will calculate the mean of all the intensities in the group 1, and then we will calculate the mean of all the intensities in group 2, and we will consider the difference. So now in terms of the noise, we also need to can understand what exactly we mean by noise. And so first thing is we have the standard, so the estimate of variation in the population, right, which will be just the sample variance. And if we would take the square root of this quantity, it will be the standard deviation. So this is just how much each data point deviates from the mean in each group, right? So I think it is pretty clear. So this is the quantity which is part of this noise in the denominator. However, because we're interested not in the individual data point, but in the mean of the data points, we actually need to divide this by the number of subjects in the first group, and then the same thing we do for the second group. So the reason I would like to emphasize this again, because Meena will be working with this today in R, right? So this quantity here, which talks about how each data point deviates from the mean, is the sample variance, is the variance in each group. If I take a square root of this, it is called standard deviation. But this ratio of variance divided by the sample size reflects the variability of the mean of all the data points. And it tells us essentially how confident we are in this mean. And so if I take the square root of this expression, it is called standard error. So this is really two different quantities which I get sometimes confused. So standard deviation tells us about how each individual data point, how far away it is from the overall mean. Standard error tells us how confident we are in the mean. And because our signal has the mean, we need to talk about how confident we are in that mean. And you see that since the sample size is in the denominator here, as the sample size increases, the standard error will become smaller and smaller, meaning that we have less and less uncertainty associated with this mean. So this is signal to noise ratio. And again, just for you to remember, we will be plotting standard deviations, we'll be plotting standard errors, just to make sure that you are on the same page about which is which. Okay, so now we build this signal to noise ratio. Very good. So the next question is, well, clearly if signal to noise ratio is large, then it's probably a systematic change. If the signal to noise ratio is small, then it's likely to be an artifact of random variation. And so now the question becomes, how large is large, right? And so this is where assumptions about our data are very important. And so what we do assume is that each individual data point is independent. And this is a really key assumption, meaning we should not have like siblings in our data, right? If we have subjects, or we should not have subjects which share some characteristics because maybe they came from one hospital and other subjects came from another hospital. So it means that each subject in our study has nothing to do with another subject in our study. We also assume, but this assumption is not really necessary, but we assume that this data follow normal distribution. This is why taking a log is useful, because on the log scale, this is much more plausible. However, even if it is not a normal distribution, it will still work. And so now, and this is really kind of the key part, so if these assumptions are satisfied, and if in reality there is no difference between these two means, we don't know if it's true, but let's just assume, for the sake of the argument, that the two groups are the same, meaning the protein is not regulated in the disease, so that we can calculate with these assumptions, we can calculate theoretically, without doing any additional experiments, what would be the plausible range of values of the signal-to-noise ratio. And this plausible range of values is described with this type of distribution. So if the assumptions of normal distribution here are verified, then this is a student distribution. If the assumptions of normal distributions are not verified, this will be approximately a normal distribution for large sample size. So let me repeat that. So if we just say, let's assume that the protein is not regulated, and if we calculate the signal-to-noise ratio, and if we assume that our data points are independent and exactly or approximately normally distributed, then we will know what to expect in terms of the range of values of the signal-to-noise. And it will be this type of distribution. And so then all is left to do is to say, okay, let's just assume some very small probability alpha called false positive rate, let's say 5%. And we will have half of this 5% on the left, half of this 5% on the right. And then we will overlay what we actually calculate from the data on top here. So if the signal-to-noise ratio falls in this middle part of this distribution, we say, yeah, well, that's what we expected, right? Because 95% of chance for the signal-to-noise be here if there is no difference between the groups. So this is as we expected, therefore there is no evidence against our null hypothesis. On the other hand, if we calculate the signal-to-noise and it's super large, let's say it's here, we'll say, whoa, it will be only 5% divided by 2 chance that it will be so large if in fact there was no difference between the groups. So this is kind of an unusual event. So this is unlikely. So we interpret this as evidence against the null hypothesis. And so we reject the null hypothesis and we say that at the false positive rate of 5%, there is evidence that this protein is differentially regulated.
Yeah, Olga, we have one question.
So let me see. The distribution should be on the log scale, even if normalized abundance is used as feature comparisons. Well, so normalized abundance can be all kinds of things, right? And if you're talking about normalizing, for example, global normalization, where all the proteins are normalized jointly to remove some differences in total signal between runs, sure, right? We just take the log of this normalization and so on. But if you're talking about normalization such as IBAC or others, which somehow normalize to the total, it actually turns out that this is not a good normalization to do for this, because what I've been discussing so far is still working with one protein. And so we'll just do these things over and over for each one protein at a time, right? And so having some kind of normalization between proteins is kind of besides the point, right? Because we're not comparing proteins one to the other, but we're comparing the same protein between the groups. So, and we will talk about this quite a bit tomorrow, but kind of the bottom line here is that we need to have normalization which eliminates artifacts for the same protein between the runs, but there's really no reason to somehow normalize across the proteins because we compare the abundances of one protein at a time. Okay, so this is for the hypothesis, and maybe just kind of to finish here. So now what is the definition of a p-value? Well, we take the signal to noise and we overlay this. So this is the observed value. We'll overlay this on top of this distribution and overlay what we observe and the negative value of that. And so the p-value is actually the area to the left and the area to the right of this observed signal to noise and the negative of the observed signal to noise. And so clearly the p-value less than alpha, so the p-value less than 0.05 corresponds to rejected null hypothesis. So is evidence against this null hypothesis. On the other hand, p-value, if the observed test signal to noise was here, this p-value would be larger than alpha, right? Larger than 0.05. And then we say there's no evidence against what we assumed. So that's really it. So this is all there is about the hypothesis testing. Now, p-values have many, many, many problems associated with them. And unfortunately, again, I don't have time to go into that, but let me just give you an alternative, right? And especially if your experiment, you narrow it down to a small number of proteins, which are of interest to you, then a really good way to report these results is not just in form of a p-value, but also in form of a confidence intervals. Because at the very least, so p-value don't tell you about the magnitude of regulation, right? It just says below alpha or above alpha. And so confidence interval, if you go back to this formula, right? So we see that we have this cutoff based on alpha, and we have the signal and the noise. We can just rearrange this expression. So this is our signal to noise, signal. This is our noise. And this is the cutoff. This cutoff is exactly this cutoff corresponding to alpha divided by 2. And so now this is the lower limit of the confidence interval. This is the upper limit of confidence interval. And so the interpretation is that if we repeated the experiment 100 times, this confidence interval will contain the true value, let's say 95% of the time, if alpha is 5%. So the limits of the confidence interval are random quantities because they depend on the data, they depend on the signal and on the noise. And so if there's a true quantity in the population, 95 times this confidence interval will contain the true value, and 5% of the times it will not contain the true value. So the reason why I'm talking about all of that is that now we discussed at least 3 ways to plot what people call error bars, right? So we can plot a value plus minus standard deviation, we can plot a value plus minus standard error, and we can plot a confidence interval. And it is important to appreciate that these 3 types of error bars will look very differently, and they will have very different meaning associated with them, right? So standard deviation talks about variation in the population, standard error talks about confidence in the mean, and confidence intervals tell us how likely this interval is to contain the true value. And so we will be doing this as part of exercises today, and you will see how different range of these error bars are. But my point right now for you is you can do whatever is meaningful for your results, but make sure you report what kind of error bar it is, because the interpretation is very different depending on what type of error bar it is. Okay, and now just in the last 5 minutes, let's go back to p-values. And so I just said that p-values have many problems. So one of which is doesn't tell you in which direction or how much things are regulated. The other problem is that p-values are only defined in the context of one hypothesis. And in our experiments, one hypothesis means one protein, right? So we want to know if for this protein, yes or no, there is evidence of regulation. But our experiments do not have one protein, they have thousands of proteins, right? And we have to do this over and over for each protein. And so somehow we need to understand how likely we are to find false positives or false negatives in the experiment which has more than one protein. And so this is what multiple testing is about. And so I'll just very briefly introduce you the reason why we need to consider that. So let's say I have 2 proteins in my experiment. And so this is my reference distribution for protein 1, I just flipped it, just for presentation, right? So here is my lower tail, alpha divided by 2. Here is the upper tail, alpha divided by 2, meaning that I will reject the null hypothesis and I will claim evidence of regulation if my observed signal to noise for protein 1 will fall into this area or into this area. The problem is that I will do it regardless of what happens for protein 2. So this is protein 2. And so, in fact, my probability of making a false positive conclusion, so claiming there is an evidence of regulation when in fact there is none, is this whole area here in the graph, right? So no matter what happens for protein 2, I'm only working with protein 1. So this plus this is my probability of a false positive for protein 1. Now I do the same thing for protein 2, right? So now this is my distribution for protein 2. This is my upper tail. This is my lower tail. And again, I only consider protein 2. I don't care what happens with protein 1. And so my probability of false positive conclusion is this area plus this area. Well, again, the problem is that we have both proteins in the study. So the probability of at least one false positive in the entire experiment is the combined area of the two. And so it's very clear, if this is alpha and this is alpha, then the combined area is more than alpha. So now suddenly my probability of making at least one false positive discovery in this experiment is more than what I would like to control. If I wanted to control it for one protein at 0.05, suddenly for two proteins, it's more. And it is very easy to show mathematically that essentially the probability of at least one false positive, it's essentially 1. So you're guaranteed, as number of proteins increases, you're guaranteed to make at least one false positive. And so this is a kind of artifact of the definition of p-values. And so in experiments such as ours, where we work with many proteins, we have to change how we make decisions to account for the fact that we have multiple proteins, more than just one. And so essentially, what we need to say is that the probability of making at least one incorrect decision, so at least one false positive, this is not a good criterion. Because what is important for us is to make sure that we can find some proteins that change in abundance, right? And we can be okay with having some proteins which are false positives. So essentially what we need to do is this. So if the combined area is greater than alpha, so what we could do is do this. We can create a new criterion which pushes our decision boundary back, so it's such that the area outside of the dashed line is exactly what we would like, such as 0.05. What it means is that we need to have some more conservative criteria. So now we will require stronger evidence, stronger signal-to-noise ratios to claim evidence against the null hypothesis. And so how can we do this? So if you have heard of the Bonferroni criteria, Bonferroni takes this alpha and divides by the number of proteins. Well, if you have alpha 0.05, and you have 10,000 proteins, it means that you have to have a really, really strong evidence, really, really high signal to noise to claim evidence of differential abundance. And this is not very practical. So instead, there has been, since 1990s, there have been a lot of research in kind of statistical methodology to say what other criteria we can use. So saying that probability of at least one false positive, it's essentially too conservative for what we want to do. And so false discovery rate is an alternative criterion, which says, okay, fine, we can have some false positives. We just want to know what is the proportion. And so this table is a classical table in kind of for this type of argument. So this is the truth. This is how many proteins are not regulated. This is how many proteins are regulated. This is our claim. This is how many we find as not regulated. This is how we find as regulated. And these are the numbers of proteins. Unfortunately, these numbers are not observable because we don't know the truth. The only thing that we observe is how many we claim as differentially abundant. So how many we reject the null hypothesis. And so Bonferroni criterion, which was saying we want to control probability of at least one false positive as very low, it translates into this table as saying we want to have a probability that V is anything by 0, being very small. So this is what Bonferroni would do. So Bonferroni wants V to be 0 always, except with small probability. False discovery rate will say, well, let's consider something else. Let's say we can have some false positives, so we will be interested in the ratio of V divided by R. So this is the proportion of true non-regulated proteins among the proteins we claim as regulated. And let's find a method which can control this ratio V divided by R and make it on average 5%, 10%, whatever we want. And so these criteria are much more appropriate for our experiments. Turns out there has been quite a bit of research in this area, which says that we can essentially take the p-value associated with our original hypothesis testing and translate this or transform it into an adjusted p-value such that the cutoff of the adjusted p-value corresponds to false discovery rate. I don't have time to tell you how it works, but let me just tell you that this would be a typical output of proteomic experiments where the x-axis is the fold change. So this is our signal on the log scale, right? So this will be, like I have it here, right? So this will be the signal, the difference between the two means. And we can think of this as a quote unquote practical significance. And this is the p-value adjusted to control false discovery rate. And it's typically transformed on the minus log 10 scale so that large values correspond to high evidence of regulation. And usually these plots, they're called volcano plots, so they will have shape like that large fold changes in absolute value are more frequently associated with higher evidence of differential regulation. And so again, the reason why I'm showing that is because you will hopefully make it to the point where you will be making these volcano plots in R today on your own. So this is all I have to say. So let me right away thank the instructors and the teaching assistants who are working very hard. And I hope some of you are taking advantage now talking to them. And this is really, as I mentioned, the crash course. Again, let me give you a disclaimer that this is by no means sufficient to kind of be efficient with statistical analysis, but hopefully this is a start if you would like to know more. So we will be offering again the May Institute in May 2021. It will be online. So keep an eye on our website and we will give you all the links tomorrow at the end of the session. Okay, so this is all I have to say. If you have questions, this is a good time to ask. And okay, so there's a fairly detailed question. So let me hold off on this one until the break. And once we have a break, I will answer. So if you have very quick clarifying questions, I can answer now. If not, we will do it during the break. So I want to make sure that Meena has enough time to talk about the R part of things.
Okay, so then I will take my turn. Okay, so I will start my screen. So can you see my screen, Olga?
Yes.
Okay, good. So a little bit overview before we start. The two main link we need. One is the GitHub one, which is already reposted in the chat. So here's a material for today. So here's the exercise, and then you can get all the material. So if you wanna try on your local, just please download the material over here. And then if you we have another options for using the RStudio. So I think that everyone now more familiar with this the RStudio Cloud. So now under the ASMS 2024 workshop, you can see the day 3, the basic statistic space. So let's just start from here. So today's my goal is start from the protein level, the quantification data, and then draw the volcano plot. That is my goal. So I hope that today, after this section, everyone have at least one PDF file with the volcano plot. So hopefully you can use this workflow like this, the whole step for your analysis, for your research after this course. So, and then we're gonna do a lot of the visualization, which came from the day 2 last week, and then also data manipulation from the day 1. So I think so when we go over this, you can review what we learned the day 1 and day 2. And then
Meena, there's a comment, sorry to interrupt, there's a comment that if you can move closer to the microphone.
Oh, okay. Second.
We can hear you, I think.
Yeah, can you hear me? Yeah.
Yes.
How about How about the sounds?
Yeah, this is better.
Okay, good. Okay, so if you in the Google Studio Cloud, now you already have everything here. So we needed these two files for practice today, and then some R script. So let's just start from the module 1. So I think now everyone is a little bit used to this comment and the R script. So any line start with the sharp means the comment. So this is just note. So we can write it down anything we want. So let's just start to here. As just a brief review for RStudio, we have 4 panels. One is our script, and then here's a console, exactly what we are running in R. And then here we can see the file, plot, and package and help file and everything here. And then here's also another space so we can see how the R have some the data set over there. So first, I just want to run the get wd, means the get working directory. So where's the working directory, which means the R need to recognize the which file is where. So working directory is the exactly the in the folder what the R recognized for this one. So I put all the file here, so I just want to set it up. This is the working directory. So here I just put the cursor here, or I can just type it like working directory. And then here they said that your working directory under the cloud and project. If your working directory assigned the different places, they cannot recognize the file, so you have to do it. Or another way you can do it here. There's a more setting button, and then here set working directory, which means that the working set this folder, this directory, what is shown in the RStudio was set as the working directory. So you can also click this one. So let's say start with the one of the data sets. So let's read our one of the CSV file. So I just put the cursor here and then run. Right? So, and then here's no message, no weird message. And then the new thing is here, now I can see IPRG data set here, which means now R have some object called IPRG, which include 6 variable and then 36,000 some observation there. So which means now R has this one. So now we are ready to use this IPRG object. So, but I want to see how it look like. So you can do just put the cursor on, hover over your mouse over here and then click it. And then it show how the IPRG look like. So this is the IPRG. This is actually have a 1, 2, 3, 4, 5, 6 column. So first column have a protein information, and second column include the log2 intensity one for that specific run. And then this run came from condition 1, came from the biological replicate 1. And then this is the original intensity. So this file, what we are working today is a protein level quantification. So this is already somehow the process the data. So if you start with some other processing tools, some intermediates that we need, but we are talk about this one tomorrow. But let's start with the protein level quantification data and then just focus on the simple statistic today. So this is the IPRG look like, okay? Then I can just close this. Then let's review what we did on day 1. So after we read, just before start any analysis, it will be good to just checking that our import our data set correctly or not. So for example, here class, it showed the IPRG is the one of the dimension means number of rows and number of columns. So here, first one is number of the row. There are 36,000 something rows and then 6 columns. This is good. Before I do any analysis, I just checking this one because it's also I can check that my file have any kind of issue. I'm missing some columns and so on. Just checking. And then the another the comment is column name. Just I can see the column name of the IPRG there, the protein column and the log to intensity column and run column, condition column, biological replicate column, and intensity column. And then day one, we also just try this head function, just show the first 6 rows. So this is also very helpful. Okay, how first the data structure look like. You know, sometimes we can just find some issue, something is not correctly read the column name or row names, and in that cases we can just change something. Tail means the last 6 rows. And then also before we start anything, just try to, oh, sorry, it is, yeah, I just used the mouse. So here, summary means just show the summary of the data set. So for example, here, the first column called protein, that it has the character values, and then the log to intensity value is a numeric value. In case of the numeric value, they just show the some summary. And then you can see here how many NA is there, what is the minimum and maximum values. You can have some idea how the data look like. And then this is the SDR structure. This is also show the structures. The first column is the character values, and then other things numeric and so on. So before you move on, you can just shortly double check your data structure. Just also kind of the small review. If the IPRD data set is really big data set. But if you want to point out the very one specific cell, one specific value, you can use this square bracket. Means, okay, this is how the R reads. From the IPRG, I want to 10th row and then second column value. So bracket row, you make a bracket and then just put the comma. The left side is row and then the right side means columns. So for example, let's practice on another thing. Let's see, I want to see just a 5th row only. So then 5 and comma, and then just make empty, means all. So I want to see the 5th column, 5th row, but all columns. So let's try to run. And it show the 5th row information. Then you can just check for this protein for this specific run, what is the log to intensity value. So you can just confirm this part. Okay, so this is, I think everyone just kind of the review what we learned the last week. And then other things, commonly what I use quite a lot is this unique function. It shows the unique information for something in the parentheses. So which means I want to get the unique information in the IPRG for a column called the condition. So basically IPRG column condition, what is the unique information they have? So I just put the cursor here and then I just run. So you can just click this button, or for Mac computer, I just use the command and enter. So here we go. So it shows, okay, IPRG condition column have condition 1, condition 2, condition 3, condition 4 have. I also do every time whenever I start to data analysis, I always check it because sometimes we can make a typo, like the condition, or we just make a lowercase or make a typo, and the cases issue out of some mistake what I made. And then before we go on, we can also just change this one. Okay, we can also find the unique information, not only for the column condition, we can get the unique information for multiple columns. So for example, I want to see the unique value in the IPRG column called the condition and biological replicate at the run. So let's try to run this. And then here we go. So this IPRG data actually have a 1 to 12 run. And then each run came from one of the condition. And then this the biological replicate. I also like this one because I can check the experiment design. So I can see, for example, here, okay, this example, this experiment, there are 4 conditions there, and each condition, they just have a 1 biological replicate, but they just measure the 3 times. So this is a triplicate. Or I can just see some different biological replicate ID. I can see there how many the biological replicate per condition and so on. So I can just review the experiment design for the specific experiment. Okay, then let's move on. So another common thing, so what we are gonna do is just select the subset of the data set. So for example, IPRG data, they have a 4 condition, 4 and then 12 one. But if I want to see only first conditions, this is the how we use. So I will just type it again. But for example, I want to see IPRG, but always break it, and then just a comma. So here, if I put something left side, means I will subset the rows. If I say, type something the right side, I will subset the columns. But I want to get all the row, including the condition equal 1. So I just put the this condition on the left side. I will say IPRG dollar sign means column, and then condition. The column name condition in the IPRG should be condition 1, right? This is the equal to condition 1. I want to get this subset. Which is the same as here. And then this subset, I will make a new object called IPRG condition 1. So let's run this line, right? Then what happened here, now we have one more data set over here. So IPRG originally, it is a 36K object, the 36K rows. But now IPRG condition 1 is a 9K, which means almost 1/4. So I can see this is the subset including only condition condition 1, or I can double check. Is this really correctly they just subsetting condition 1? So unique IPRG condition 1 and condition. So which means I want to get the unique information of the condition column in IPRG condition 1, right? And then click run. Now it said this include only condition 1. And this is this condition. I mean that this condition means this condition. We can add more. So here, the other case is I want to subset of the IPRG, which include the condition is condition 1 and the biological replicate equal to 1. So in that cases, you can just use this and sign over here. Okay, so I think this is the kind of the review what we did the day 1. But let's move on to a little bit more. Before we start, we have to use the tidyverse. So I hope everyone has this one. And run. Okay, so next step, what I'm gonna do is we just want to change the format. So if I come back to the IPRG, here IPRG, each column have each unique character. So for example, this column have an intensity is a numeric value, and then this column can have the character or vectors and so on. So all the intensity actually only line up, only just one line here. Commonly we call this is a long format because it's kind of the really long. It's a narrow, but it's long. But this is a quite good format for if you want to use the tidyverse, the packages. But commonly the processing tools generate the data set as a wide format. The wider format means row have some unique variables, and then column have also another unique variable. For example, the row should be the proteins, but each column for each run informations. And then body part include all the log to intensity, just all the same, the numeric values. In that cases, if you want to use the R, you have to transfer wide format to this type of the long format, and then you can go over it. Or sometimes you want to change this long format to the wide format. So I just try to do this first. So here I will use the spread function from the tidyverse, the package one. So if you want to see what this spread function, just run it, and then it will show how we can use it. Today is just 3 hours, and then total we have 4 days, but we cannot cover all the functions. So whenever you want to use the new functionality, you can find, searching the function, and then always check the help file, what kind of information they need and what kind of options is available. So, okay, here's how I did it. So the spread, I just used the spreader function, but let's just run the first line. The first line means if you just, I just want to remind what is this pipe. The pipe one is for the tidyverse, the package one, means from IPRG, I want to select protein run log intensity columns, right? So I will run this, right? And then put this one as the wide IPRG. So let's say now we have a wide IPRG data, and then I just click it. Okay, so now we have only 3 columns, right? We can check it here, and then we also can check it here. So if compare IPRG and wide IPRG, we have same number of the row, but much smaller number of the variables, 3 columns. Then, okay, I also add one more thing. Okay, from there, from IPRG and select from there, and then I want to spread this data set by run, and then put the log intensity value in the middle part. So I will run this one again, right? Then, okay, so here, what I can see before actually we look at the wide IPRG, now we have a completely different number of the rows and then different number of the columns. So let's look at this. So let's look at this. So now here, this is the wider format. The column, the row is for each proteins, and then each column is for run, right? And then the middle part is the log to intensity. So for example, here, first one is for this specific protein for this specific one. It was the one row before in IPRG. This one is for that specific the proteins, and this is this specific the one, and it actually has the one row before in the IPRG. So this is the wide format, and then probably you see this one more commonly from data processing tools. Then just another practice. If you have this wide IPRG format, let's transfer to the long format. So here, this is how we can do it. Now, let's start from the wide IPRG, but we use the different function, gather. We use the gather function. I want to gather wide IPRG data set by run, and then I just put the log to intensity as another column. So let's try to run this. Now we have a log IPRG, long IPRG, and then you see now the number of the row for long IPRG is the same as here, and then different number of the columns. So let's double check this, and then see now we have we are just came back to the original one. But difference is, here this is the long IPRG, and then here I just type the head IPRG. Now we have a much more information, right? So for each run, I also want to add this condition and then biological replicate information. We can do that. We don't need to write everything just by hand. So we can just do it. Basically, we can merge this. So if we have some information for each run corresponding to which condition and which biological replicate, we just automatically run it. So that is the what we have annotation. So let's run this one. And then let's look at how the annotation look like. So this is the much small set, which include each run have a which condition information and then biological replicate one. So now we have this annotation, and then now we have the long IPRG, which have only run information. So we want to add the condition and biological replicate information in the long IPRG. We can use the left join function. So which means, put the left side, this is a long IPRG. This is our, basic data set. And then want to join information from a node into the log IPRG by run. So the run column information is kind of the intermediate, the buffer. So based on if the run information matching, we are gonna put the annotation information into the IPRG. So here I just run, and then now we can see that this new IPRG have this information and then the condition and biological replicate informations. I think everyone is so far good. Yeah. So, during the TA section, if you finish the exercise, you can start use your data set. You can start to read your data set, and then you can just try to practice to just change the format. It looks very simple. However, the many people actually stuck at this point. So if we have to make the data structure is more familiar with or friendly with the function, we can just use the function in the next steps. So I think I need to speed up a little bit more. Okay, so let's say just a little bit review for the visualization. We practice about the ggplot. This is the layer structures, right? So here always is a plus, 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 plus. So let's say first ggplot, this is a kind of the basic function. We have to say, I will use the which data set, and then what should be the x-axis or what should be the y-axis first. So I just select only this part and then run it. And then this is show, this is the empty, but this is actually already assigned what is x-axis and then what is the y-axis should be, right? And then we just want to add next one. We just add the dot over there, right? So, okay, here's our base. And then just add one more. Now you can see, okay, we add a dot as a jitter. And then we make the color by condition information. And then we want this size and this alpha. The alpha means a transparency one. Okay, so we have this. And then over there, I want to add the box plot. So here, I add, again, here, the same thing, but we just overlay the box plot over the jitters. Okay, that's okay. That looks good, but I want to change the labels. Label y-axis and then x-axis, and then also add the one to title. So here, I just want to add the label here. Yeah, I can. Yeah, so here. Now you can see it's getting different. So now we have a title. We just changed the y-axis and x-axis. So, but I just want to change the theme. The theme means, you know, kind of the background, the color, like the basic options. So I just want to minimize this one. So this is also one of the type of the theme. Now you can see the background color is the changed, right? And then the last, I want to change, you know, it's really hard to read the label in the x-axis, okay? Then I just want to change these angles. So in that cases, I want to change the theme. I want to change the x-axis, the text, which text, x-axis, text, and then I just want to change the angle is 90 degrees. So let's run, select all, and then run. Now we can make this one. So if you want to change something, you just keep adding just a plus and something and plus something and plus something. So you can keep adding the options. So I think this is the kind of the one plot, but this is what we draw the date to.
Yeah, there's a question how to change the color of just one condition.
Just for one condition. Okay, that is the good one. If you want to change the one color, we actually need to change the color scale differently. So for example, here, scale, color, manual. Then I just want to give the value. So for example, here, let's say red or yellow, blue, purple, right? Let's see, this is working. Oh, right. So now only what changes is the back. Yeah, this is the background one. So why? Because, you know, here you can see jitter is, you mean the dot. This is the bicolor. Box is means field. So this, the box is, we call this is not color, we call this is the field. So if we want to change this one, we can also change the same thing. I just copy here, but I want to change the scale of field manually, and then the value will be this one. So I just, this is a comma, means they are not going to read this line. So let's see how it goes. So this is how it goes. Good question. So yeah, so day 2, the Kylie also showed some palette, which means they have a really good combination colors. Also, you can call that palette for this one if you want to make a really nice, the fancy color one, or you can also define your color. So you can use the red, yellow, or something, but also you can use some number of their color things or RGB number or something. So many sources there. So we can just search in it and then can use it if you want to make a nice one. Yeah, we will have a many chance to practice this change visualization today. Okay. How to center the line. I think so over here, the theme, maybe title something. We can search in. Yeah, I was searching during the break and then let you know. Yeah, there's so many options there. So always when I try, I also just searching the Googling and then just put the cheat sheet there and then just change the options. Okay, so that is the the experiment design, randomization, replication, and so on. The common question is, yeah, I know we have to randomize, but how we can do it? So here we can use some function called sample, which means they wanted the sampling. So for example, here, sample function, what they're doing is from 1 to 1,000, select the 10 value. Okay, so I just put the cursor here and run it. They just select the 10 value here. I will just, let's see here, the simple case, the sample 10, 3 means among 1 to 10, select the 3 numbers, right? Here, the 4, 8, 2 are selected. Okay, I just want to run again, different number selected, right? Here, run, different number selected, right? So if we want to keep whatever our selected value, there's a way we can set the seed. It doesn't matter what numbers are. If you set the seed and then run, now you see here 1, 9, 10 are selected, right? Then let's run this again, 1, 9, 10, right? And then select again, 1, 9, 10. So if we set the seed, even though sample function, they just keep the same selection. So for reproducibility, or do you want to keep the record for your selection? If you want to use the R, set the seed and then sample on the, okay, here's the 1, 9, 10 are selected. So I think it will be good to keep the record of what threes are selected for later and so on. Also, not only for number, we can also select something like, character value. So let's say 1, 2, 3, 4, 5, 6. So all our, the lectures are there. And then we want to select the 3 people. Want to select the 3 people. So here, if you remember, this group members, now this is the vector, have a 1, 2, 3, 4, 5, 6 character values. So in this group member, I want to select the 3 people. So same thing, sample group members and 3. Now Matthew and Melanie and Ryan selected. If you run again, the Matthew, Olga, Kylie selected. So commonly, when I make a joke, when I was the grad student, we need some proctor for the final exam on the Saturday. In that case, not many people want to do it. And then we just put our name on it and then just use this, the sample function, and then select the proctor for Sunday or Saturday in the morning. So, okay, how we can use this? So for example, let's come back to the IPRG run. So now let's imagine you have a 12 MS run, but we need to decide the order of injections, order of the injection for instrument. So we need to randomize it. How we randomize it? We can use this one when you decide it. So for example, here, I will get the unique run information here, right? And then MS run is a vector, include the 12 MS run information, right? And then over there, I just randomized this order, completely randomized this order. So I just used the sample, and then from the MS run, but how many selected? So previously we just select the 10, 3, but what here, sample 10, 10 means 1 to 10, we select the 10 randomly without the replacement, which means we actually can select the orders of the 10 numbers, right? So here, same thing, MS run, but the length of the MS run. So it means how many values they have. They have a total 12. So MS run just we just want to select the order. So here, let's say the first one is a 4C and 2B. If you want, again, now we have a different order, the 4B and 3B and so on. So this is the completely randomized order. So among the whole 12. So it doesn't count any condition or doesn't count any batch. Let's assume we have a 1 day, and then we can measure the all 12 MS run, and then what is the randomized order. In the cases, we can use this one. But let's move on to a little bit more, the randomized block design. So let's say we have a 12 MS run and across the 4 condition, but we can measure only the 6 MS run a day. So today we can measure the 6, and next day, tomorrow, we can measure 6. Or more further, like if you have a really large scale, we can measure 100 one day, and then like after a few months, another 100 something. Then means if you have a total sample, we just want to make each block, and then within each block, we also want to randomize this part. So that is the kind of the we can do it. So for example, here, we have a total 20, let's see here, we have a 12, total 12 the MS run, but we have a for group. And then here we can use the block random, the function. This is from the Psi package. So here run, and then let's run this part. That means we have a for group, which means we have a 3 blocks can measure. For each block, we can measure the all groups, but within the block is completely randomized. So for example, here, first the block here, and then 1, 2, 1, 3, 4, 2, 4, and then next block 4, 2, 3, 1, and another block 1, 4, 3, 2. So each block they just randomized this the group information. And then for example here, we have a bigger scale. We have a 24, but within 24, there are 2 groups and 4 time point and the 3 replicate information. Then it shows, okay, you have a 24 block, 24 samples, and then this is the how you have to randomize it. So they actually consider all three factors and then randomize and then show how to do it. So for example, first you have to measure the sample from group 1 time point 2 and replicate 3. Next from group 1 and then time point 3 and replicate 1 and so on. Okay, so this is a simple case for your experiment design. A little bit think about it, but this is also might be one of your tools so you can set up the experiment design. So let's move on to the real calculation things. Okay, so IPRG data, let's see. First, let's see IPRG data, how many proteins they have. This much unique the proteins have. Oh, so many, there's no count. So I just want to see how many itself. So then I just say length. What is the length of unique information of IPRG protein column? Run it. Here we go. We have more than 3,000 proteins there. And then for then my goal is I want to calculate some mean value for one specific protein. Let's just start from the one specific proteins. So here I would choose this proteins. So let's make the new object called one protein data, which include only the protein, this one. So from IPRG, I just type again, IPRG, I want a subset, okay? So, square bracket and then comma. I want to get the row, include protein information, IPRG protein information equal to this, right? So then on this subset, I want to call this is the one protein data. So let's run this one. So now one protein data, let's click this. However, one protein data, okay, so only one protein, so same protein, but different, a total 12 MS runs. So now this protein, we have a 12 run and then 12 log intensity. It came from the 4 different conditions, right? Let's just start those simple things first. Or, okay, there's a two-way. I just want to address a two-way. So this is the one way we can do it. Or if you want to use the tidyverse one, this is also same way. Same thing. So from IPRG, I want to filter the row which protein equal to this information. Let's run it again. Because we have a same object. If I run later, it will overwrite. So the one protein data is based on this comment. However, we're gonna have the same information because this is basically the same comment. Okay, so now one protein data have a one protein information from the condition. Let's say I want to compare the mean value per condition. In that case, I will use the aggregate function. So this is kind of the aggregate function, means we split out this data. We split the data called the one protein data by condition, and then compute, this is a fun means function, compute the mean of log to intensity, right? So let's run this, right? And then some mean show, okay, from one protein data set, we can calculate the mean of the log to intensity for each conditions, right? Same thing, see here, same thing, but I want to calculate now, I want to calculate the standard deviation here. So aggregate the same things. Right, so the filter function is for the rows, but the column function, we can use some different one, select. The select, and then we just put the column name, and then we can just use the column one. On the second thing, so same thing, but I just want to calculate the standard deviation, same thing, but just function, I just changed the function as a standard deviation here, and then run. Now standard deviation have this information, right? And then something else, so same thing, I just want to calculate the length. Length means count, how many values they have. So here, count, show, yeah, they have a 3 log intensity per each conditions, right? Then, okay, so unfortunately they don't have the R does not have a standard error function, the embedded function. So in the cases we have to calculate it. So this is basically the from the formula what the Olga showed. So I think it would be good practice for calculate the standard deviation, which means if you have your own equation formula, you can also just calculate in R. So here, standard error calculate by square root, and then inside the standard error as the standard deviation square root, and then divide by n. So here is the function square root is sqrt, and then this parenthesis, here, if you put the cursor here, you can show what is the end, right? So from here to here is under the square root. And then, this is the division, divide by, right? And then the upper side is numerator, it should be standard deviation and square. And then denominator should be just length equal n, right? And then based on this formula, they just calculate the standard error, right? And then now we have a mean values, standard deviation values, length, and then standard error. Then we can combine this as a one data set. So how we do it is data frame means I want to start to make a data frame. Okay, and then here, this is the parenthesis from here to here. So this data frame should include first group column, second mean column, third standard error column, and the next standard error column, and then the last column is the length column. And each column should have these values. So for example, group column should have this condition 1, 2, 3, 4 information. And the mean is from what we calculate, then the mean, and then their log to intensity, the columns. So let's run it. And then summary result, here we go. So first column is a condition, want this information, you see 1, 2, 3, 4. And then mean column from what we calculate in the submean. And then here's a standard error, deviation and standard error, and then length. So now, we have a nice one. And then we just get a very simple statistic. And with this one, we can, draw the visualizations. Okay, so if you use the aggregation function, it's quite long, right? So we can calculate the same thing with the tidyverse, the package one.
here from, it looked like the lengthwise is quite simple, right? So here the one protein data set, in the one protein data set, I want to group by condition, which means I want to split the one protein data set by condition information, which means now we have a small set condition 1 for small set for condition 2, small set for condition 3, small set for condition 4. Then for each subset, I want to summarize. This is the kind of same function, same concept of the aggregate function. For each subset, I want to calculate the mean log of the log to intensity, mean of the standard error, standard deviation of the log to intensity, and then n is the length count, and then just make this. So let's run this one again, right? You don't need to worry about this, the message one. Okay, here we go. So now from one protein data set, by each condition, they calculate the standard, the mean and standard error and length, right? The standard error is, as I mentioned, we have to calculate, right? So in that case, we just add one more one. So how we do it is we can use the mutate function. Mutate means in the tidyverse, we want to make something new one from the whatever we have in the data set. So which means from summary result, we want to add one more column called standard error, which how we calculate it. We want to use the SD. SD means from this column in the summary result, and then use this length. So let's run this. And then here we go. Now we have a standard error, the value. So let's see, let's compare what we calculated before used aggregate. So here, this number, yeah, you don't need to worry about this number of the digit. They actually have a more accurate, but this is just how they show it. And then here also, here's the same thing. This is, they just round up just to show, just to print in the console, and then length is here, same, and then this is the same. So same numbers. So it's up to you. You can decide it if you, yeah, it looked like a much simpler. So you can just decide either way you feel comfortable. So now the next one is, okay, now we have these numbers. My goal for next step is I want to draw the plot with mean and error bar. That is my goal. So let's come back to the ggplot. So here is the basic one. So first line is a basic line. Always start from the ggplot and then parenthesis. And then we have to add which data set. I want to use the data set called summary result. And then from there, x-axis should be the condition and the y-axis should be mean column. This mean column, I just put the mean value over here. And then I want to change the color by the conditions. The break, yes, so I will go over a little bit more, like just visualization. It will be this last step for this module. So after this one, we'll have a break and maybe start the TA sections. Thank you. So here, ggplot, I will start ggplot here, just make a space. And then over there, I add the point. So here, we just start the point, right? And then, automatically they just show this legend because I want to color by the conditions, right? And then I just want to change a little bit more. So here, you don't need to worry about it. This one is pretty much just a background of what I want to change. It just add some columns. Yes, this is the tidyverse. The first I'll show, yes, the first one I show is aggregate function, which is not tidyverse, the package one. The second way is when I use the pipe, this is always the tidyverse, the package. Yeah, so this is just basically, I just changed the background, right? And then I just changed the legend, the location. So for example, theme. Theme is pretty much how you organize this background thing. So for example, I just changed the title size and text size. Text means this. And like, for example, condition 1, 2, and then 21, 22 stuff. And the X is title means this title, these titles. And then legend position, previously we have a legend on the right side, but I just want to put legend in the bottom here. And then also change some background and key, like there are so many options there. But this is what I want to right now, but you can change anything you want, right? It's the same thing, but some here I use the dot one, but I know that some people like the bar plot. So in that case, I just pretty much copy everything, but only one thing is difference here. If you compare here, I use the geom point, but instead I just use the bar, and then other thing is the same. And then here I just run. Here we go. This is the bar, right? And then, only difference is I just make a color by condition. So you can see that this line of the bar is the what they call color for the bar plot. If you want to change inside, you have to change, so this is a fill. So let's see, fill, condition. Here we go. So we can change this, the box colors. Let's move on. So let's come back to the point dot plot one, but I want to add the error bar with the standard deviation. So what I did is exactly same as what we draw this one. This is from here. I just want to add the error bar. So here, what I do is this line. I just add one line, one layer overlay. So here, error bar comment. And then here's the parameter we have to put it is here. What should be the upper side or what should be the lower side? So upper side here is I just from the mean plus a standard deviation. The lower side is mean minus standard deviation. I added. So here we go. So now we can see the error bar, right? If you think is this the error bar, the width is too wide, here width options. So I just changed it to 0.1, and then here we go. This is how we made it. Or I want to change the error bar by the standard error. It's the only difference between here and here, everything is different, but here, this is the what we calculate in the summary of the result one, right? So I just changed this SD to SE. Now you can see we have a much smaller, the narrow the error bar here, right? Just really last one. So we talk about standard deviation, standard error, the confidence intervals. To confidence interval, our summary result we didn't calculate it. So here we have to calculate the confidence intervals. So this is basically the formula what the Olga present, mean plus minus, which means this is lower and upper one. Upper one just t distribution, and then based on the percentage, this is just basically the the equation. Only things we have to aware of, this is a 95% confidence interval. This is the two sides. We have to think about the right side and the left side. So when you define this, you have to divide by 2. So for example, 95, so left over is a 5%. So half of the 5% is 2.5. So you have to 1 minus 2.5, it should be 0.975 for lower side and the upper side separately. So I just run this, right? And then now we have a lower and then upper value there. Then same thing, exactly same visualization code, but difference is only just maximum and then the minimum value. So here, just run. Now we can see it's also wider. and but you can just easily change this error bar. So I think yes, it's already take long. So you know, the exercise in the Google Cloud, you can see module 1 exercise 1 here. I just make some note here. Please go through. You can also come back to our original one. Feel free to change. And then, you know, last week, I hope that everyone have at least one of this plot as a PDF. How to save this one, you can ask a TA, or you can also come back to the two material one. So I think that for right now, I will give you the 30 minutes. Let's come back the 2:15, including your break and then the TA exercise.
Sounds good. So it is 1:40 Eastern now, so we have 35 minutes for the TA and the break. So please check the TA link in day 3, right? Make sure you go to the right link for the TA. If you have questions to us in the main room, we will also hang out here for a little bit. Probably Meena needs a break as well, but I'm here if you have questions to me. And so what you can do, you can just kind of either put the question into Q&A, or if you have like a longer question, let me know and I should be able to give you a voice ability so they can actually ask the question in speaking. So, but otherwise, I hope that don't hesitate, please go to your TAs and you can work out essentially for all of those things. You can make your own plots. I think that this will be very useful for you. Okay, so if you don't have GitHub installed, so there's a question, how do we download updated GitHub for this course within RStudio?
I think
Meena, maybe you can answer.
Yeah, if you don't have a Git, you know, it's not automatically we can update it. I just recommend just download, you know, you can see my screen, right? Right, so here our GitHub link, and then go to the code and download zip. So, which means it will download the day 1 and day 2 again. Yeah.
And I also think that for the documents, you have Dropbox, right? So you can also just go to the Dropbox link. Okay, so let's see. So Valeska, so I think you should be able to speak. So if you have your question, you can ask it now if you would like.
Hi.
Hi. Yes.
Hi. It's nice to meet you.
Nice to meet you too.
Oh, well, my question is a little longer. It's about like input missing values in the data frame. So sometimes when I have a bigger data from proteomics, I have like the search for by MaxQuant. So sometimes we have like in biological replicate some values that the machine does not detect, or something that the protein is not there. So sometimes when I do the global normalization, the group normalization by MS Stats, I saw that some values I don't have numbers in some proteins or in some specific groups. So I'd like to know what's the best way that I can input some values on the table that I can calculate the test or calculate or continue the data analysis. Because if I have like a missing values in one or two biological replicates, it's like difficult to do the test, for example.
Right. So, okay. So my first answer is let's hold off this question until tomorrow, because we will be talking about imputation and MS stats tomorrow. So I think that will be the best way. Although, you know, again, we have such a limited time for everything. So we will just do, you know, like vignettes on what we can, right? But
Okay,
kind of more generally for your question. So missing values are tricky, right? Because you need to kind of understand if they're missing at random or they have some information behind them, for example, because they're missing for some systematic reasons, such as low abundance. And imputation essentially means making up new data, right? And then your method thinks that you have more data than. So you have to be very careful. And usually in MS stats, we impute it only when we have evidence from other peptides of the same protein and other runs of the same peptide to understand what the value would be. But all of this you obviously want to do before doing statistical inference, so before hypothesis testing, right? Before all of that, because once you have a p-value, you are done, right? There is not much else you can do. But there are multiple issues, like in terms of normalization and imputation. So let's wait until tomorrow. So hopefully we will be more on the same page.
Okay, perfect. Thank you, Olga.
Thank you. Okay, so and then we have another question. If in general it is correct to calculate the standard deviation on log transform data. Well, you know, you can calculate standard deviation on anything. It's not like you can't like technically do it, right? The question is how you are going to use it, right? And so what are you calculating it for? So if you want to illustrate the extent of variability in your population, so standard deviation would reflect that. But imagine that you have data which are not symmetric, which would be the case if you have original intensities, right? So usually you will have a distribution which will be, I don't know if you can see me, like it will be very skewed. So you have most data kind of around low values, and then you will have some outliers with very high values. So the standard deviation is just the average deviation of each point from the mean. And if you have the outliers, many values together, and then some outliers, the mean is pulled towards outliers. The standard deviation is influenced by the outliers. So it essentially does not reflect the true variation in the data, just because there's so much asymmetry. So standard deviation is most informative when the distribution is close to symmetric. And usually log transformation, it will not be perfect, it will not be exactly normal, but it will be closer to symmetric, which means that standard deviation reflect the variation better, but also the assumptions necessary. Remember, like the signal to noise ratio I was talking about, right? And how we are confident in the mean, it will reflect this more accurately. So I guess the answer is yes, right? But primarily from the perspective of how you are going to use the standard deviation. And also, I hope so. The reason Meena went so long with her presentation today, because we really wanted to illustrate standard deviations versus standard errors versus confidence intervals. And so as you work with exercises, so pay attention to that. I think that's really one of the main points beyond just how to do it in R. So if you're joining us now, we're on a break, and everybody is encouraged to take advantage of the teaching assistants to go over some of the exercises and answer questions. But if you have questions to Meena or me, we can also answer this during the break. So yeah, there's no equivalent of a hallway conversation, so we try to do it as we can. So don't hesitate to ask in the Q&A. We will start in a couple of minutes. And Meena, there is a question for you.
Right. So Bini, I just right. So one of the questions what we have the first section, how we can align the title in the center. So here I found this. So basically how I found it, I will just show you just for reference. So I said ggplot2 theme title alignment, right? And then here they just, there are a lot of the sources and solution in the web already. So here is the key. So we can use the H horizontal adjustment 0.5. I guess it should be 0 to 1. The 0.5 is middle, but this should be in this one, plot title. So what I did is come back to our plot here. So previously, this is the what we have. So we already have a plot title, so element text aside, and then change the color as well. Then I just type here, add one more adjustment, H adjust, and 0.05 is, this is how I did, right? So now we can see this middle. The question about the broken y-axis one, definitely there's a way to do it. And then I remember I performed this one before. But just during the TA section, I was searching what is the best way to do this part. Okay, so I think so we can start for the section 2, module 2 for sorry, I just keep just using the pen. Okay, here we go. So section 2, my goal is make a volcano plot. So at the end of this section, I hope everyone has one PDF file with the volcano plot, right? To make a volcano plot, we need some result for hypothesis testing, and not only for one protein, also for all the proteins, right? So first, I will start with how, here I just want to show how we use the t-test, one of the basic test one. And then from this test, how we can test for across all the proteins, and then how we adjust the p-value, the multiple testing correction one, and then how to make a volcano plot. So before we move on to all the protein, let's work with the one protein case. So just in case, this is the subset, the small set of what we made at the first section. I just select only this part, and then it shows here. Here is the what one protein data has. It has 12 rows for one specific protein, and the log intensity group and condition and biological replicate information. For t-test function is only performed the 2 different conditions. So now we have this one protein data have only 4 conditions. So I also need to subset for condition 1 and 2 again. So there are several ways. So 3 different ways you can choose, so whatever you want. So first way is I will just type it here. Okay, just how I just wrote the code. So from one protein data, I want to make a subset and square bracket and then comma, right? I want to get the row which include the condition information. Protein row is a condition. Information include condition 1 or condition 2, right? This is a kind of include, either of this include the condition 1. But here's a little bit tricky, so it's a which. 1. So let's say I run, and then it just showed the subset, the 6th row, which have a condition 1 or a condition 2. Other way, we use the tidyverse, pipe 1. So from one protein data, we want to filter condition include a condition 1 or condition 2. Or other way, we can just say filtered condition value is equal to condition 1, or this is the pipe. In the keyboard, this is the pipe sign. Piped condition equal to condition 2. So any of this is working. I just run one of this, and then sub have a 6 rows. Let's double check the just practice again. Subject, object, which unique information they have. It has only condition 1 or 2, and then previously it has a condition 1 to 4, right? So for solve, using this solve, I want to test between condition 1 and condition 2, their intensity. So here's the function called t.test. This is for the t-test 1. So whenever I met the new function, I always use the question mark and t-test. So I just run this. It shows health file. Here, health section, it shows the health file. All the functions should have this file to explain what kind of the parameter they need, or what kind of input they need, or what kind of option they have. So for example, here, t-test. So t-test need a data set X, and then there are some options. So here's the option alternative, what alternative hypothesis they can handle, paired and variation equal, confidence interval, and so on. So to know the detail about this, we actually have to look at their explanation here. So conf that level means confidence interval, confidence level of the intervals. The VAR equal means they just can have assumption the equal variance or not, and so on. So because depending on what option you choose, actually the result is different. So that's why I just recommend to check all the health file, especially for statistic part. So let's here look at a test, t-test. I want to use the data subject, and then what is the formula? I want to compare the log intensity between the condition, and then I want to unequalize the variation assumption. So let's run this. So now we have a run. And then here you can see it looks a little bit different, right? So here always show the rows and the column information, but they call this is the list one. So I think you don't need to worry about this format-wise. But the one thing is very clear is that this result is not a table. So what we can see, for example, it is not like this format. So what I can see is so all the result is saved as a result. Let's run and what the result is. So result include all the information about the t-test. So it actually has a t statistic value, it has a degree of freedom value, it has a p-value, and it also have a confidence interval for 95% one. And then it has the sample as the mean value of the condition and mean value of the condition 2. So, okay, this is good. This is how they just, the print and then present their result. But, we can test it, and then we don't want to copy every single value in somewhere and so on. We just want to extract this value from the result and then save it as the nice format. So here's another one. If we want to change the confidence interval part, you can just use this option and then change the one. So default is 0.95%, but you can just change this as 90% or something. So let's come back to the result. What is the result? So let's see how this result look like. As I mentioned, this is another data frame one. Names show the result to have what kind of element they have. So it showed the result had a statistic element, result include the parameter element, result include the p-value and element, and so on. So they save this one is separately, and then when they just present in the R, they just make this nice format. So let's say if you want to see each element, you can still use this dollar sign. So for example, here result dollar estimate means from result what this estimate has. So let's here run. Yes, the estimate have this mean value. So this is the first one, and then this is the second one. So for example, here result estimate, and then square bracket, and then first one. So what is the first element of that result and estimate? Just run it. Okay, here the first element has this values, and then what is this? The second value is the second value. What is so if we extracted this value and extracted this value and then just subtract, and then this is the low to for the change between condition 1 and condition 2. So same way on the result dollar and statistics. This is include t statistic value for one. And then actually, here they do not provide a standard error, but actually we can calculate the standard error from here. So how we, if you think about how we can calculate the t statistic, estimate 4 changes and divide by standard error equal to t statistic. So I just tweak the change on how to calculate the standard error means this difference, and then divide by the t-test actually can show the what standard error they use it. And then the result parameter is show the degree of freedom, and then result p-value include their p-value from the t-test, and then also confidence intervals, and then so on. So, okay, so here is the t-test output. And then this part is how we calculate manually calculate the t-test result. But I think so we can just practice this one is if we have extra time. So let's move on to the next step. So this is the only one t-test for one proteins, but I want to run this one for all the proteins. So if you remember what we practiced here when we draw the mean and then error bar, we practice with the 1 proteins. We can also calculate this one for all the protein. Just use this small line, the 5 line. If you compare these 2 lines, what is the difference is here. Previously, we calculate, we actually have 1 proteins and then just group by condition, and then just calculate the mean, standard, and the count. However, if you start the whole protein, which include more than 3,000 proteins, if you group by protein and condition, they just make a subset by the protein and condition, and then just calculate the mean and standard error, and then the count. So let's run this line, and then let's look at how the summary all look like. Here we go. So this is a summary all for one protein and each condition. They calculate the mean and standard and length. And then here you can see for one protein, we have 4 conditions. And then next, they just calculate for the second protein and including everything. And then this much row they have. So this is how we can calculated for everything. And then also same as what we calculated, just to use this mutate function, we also add the standard error and then confidence intervals calculation. So here, run. Now we have a standard error and then low and then upper one. So previously we practiced, we can calculate this one for one protein, but we also can calculate this one for all the proteins there. And then, okay, so then we can also plot all the proteins cases. Previously we have only one plot, but we can plot the same plot for all the protein and then save this as one PDF files. So to do this, I will just introduce the the four loop functions. So in R, if you want to do the repeat the same calculation across the different cases or multiple times, we can use the for function. So for example, I will just type it here. How I started always the for, and then start the parenthesis, and then another parenthesis here. So what we have to put it in here is that here in this parenthesis, we have to show how many times we have to go through this part. So for example, I just start I value in 1 to 10. Means first I value should be start from 1 and then perform whatever inside here. And after done, I value move to the 2. And then just to repeat the same thing what happened in here. And then move to the 3 until I become a 10. So let's say here, the print function means just show just printed in our consoles. So here, I want to print I. So for example, here I first will be the 1 and then print 1. And then next I will be the 2 and then print 2 and so on. So let's see here. Just, we just see the 1 to the 10, but if each step have a more complicated, you can see how, they are moving 1 to 10. So we are gonna do this, the for loop to repeat the same plot, one. So here is what I tried. So here, let's look at the first here, this part. So I want to repeat the 10 times, 1 to 10. So I will be 1 to 10. The first, what I'm gonna do is from the summary value, which we already calculate the mean standard deviation for every proteins. From here, I will get the first proteins, and then it will be just a subset. It will be the small set. And then for this small set, I will draw the plot. This is the same plot what we practiced. And then I just add the error bar for confidence intervals. And then I just print this one. So P means I save what we draw in the P object. And then after P, and then add this and then print this object means print this our plot. And then next time I become 2, and then I will just get the second proteins and then draw the same thing. And then move on to the I equal to 3, which means the third protein, and then repeat until I protein 10. Okay, so this is what we can practice. Let's run it, and then let's see what happens. You can see there's a plot. You can see every time they just draw the different plot one here, this side. So if you come back, it will show what we make this plot, so you can see the protein names are different. But I want to save everything in the one PDF one. So here is how I did it. So PDF function means try to make the PDF function, start to make a PDF function. So here means I want to generate a PDF, call this file name, and then this much width, and then this much height. So okay, I will start to generate the PDF. So they start to do it. And then they just, draw draw the whole 10 every single time, right? And then the div means, okay, then close it. I'm done. I'm ready to just finish the PDF file. So let's select from here to here. Then you see here, and then here, the red button means stop, means make a stop. Right, and then this is the done. Then let's come back to our file. So previously we have only R and then CSV file, but now we have the PDF one. So whenever you generate, save something, it will be saved in your working directory what you assign at the beginning. So let's click this. So now here we go. So this PDF PDF have 10 pages. Each one have the plot for each protein. So this protein is how it look like, and then this is the second one, and then this is the third one, and so on. So you can generate everything in the one PDF. Okay, so we now know the group, and then we just practice how we can generate the what we calculated. Then let's come back to the t-test. So previously we practiced how we can t-test, how can we do the t-test for one proteins, but now let's combine the for group and then t-test part. So this part from here to here is how we test the t-test and then save all the result in the new the tables. So first what I did is I will get all the protein ID first. So I want to get the unique ID, unique information of the protein in IPRG, and then this unique ID will be saved in the pro list. So let's run. And then pro list, how it look like pro list. This is the one vector, and then it includes all the 3,000 protein informations. Right here, pro list is a character, and then it includes the 1 to those more than 3,000. Then next one is what we have to do it is we need to start to we need to create the new data, the metrics, which we can save all the output from the t-test. So here, I want to make some new table called all result, and then it will be the data frame. In this data frame, I will make a 3 column. The first one is a protein, second one is the t-test, and then other thing is the p-value. So let's run. And then let's see how the all result look like. So here now I don't know any value. So I just make this is null, which means empty, but I just start to make a structures. So in the data frame, I just define the column, which column I need, but in the actual value, we don't have it. But this is already there, but just 0 column and 0 row. So that's why they couldn't show it, but they have it. So then my logic is, okay, here's the loop part. So for loop, I will be from 1 to length of the protein list, the length of the protein, which means total number of the protein. So I'm gonna repeat from first protein to the last proteins. So for each protein, I'm gonna perform this part. So let's say I equal 1. Let's just say here I equal 1. Let's see when I equal 1 what happens. So I equal 1. I equal 1. So here it is. From IPRG, I want to get subset of the protein ID equal 1, right? So here, how will it look like? See? Yeah, so they just subtract the first protein. And then for this, I want to also substitute again for condition 1 and condition 2. Right? So now we have a 6th row. And then if they have a NA value, missing value, I want to filter them out. So filter, and then if log intensity value, this is the is NA, which means it's just NA value. Or if you put the just a question, this mark, it means not, it is not NA. So I want to use only intensity value is not NA. So let's run here and then see how the subject look like. So here we don't have any value, so they just use this, all 6 rows. And then for this subset, as we did before, I just run the t-test and then result look like here. But I just want to extract the very important information what I want, and then add this value in the what we have. So here, first I want to make some template which include this subset protein ID, and then this the log 2 4 changes, and then t-test, and then p-values, right? So let's run this, and then how the TMP look like. It has, this one has information for this protein, and then result from the t-test. Then I will add this information to the data frame, which I want to saved all the information. So here, and then now all result have this information. Just in case, I will show what is the next time. So after this, and then they just print I equal 1, and then this is done. And then they come back to here, then now I become a 2. So I equal 2, right? Then let's see, I equal 2. Now we have a new sub, the new sub 1, and then they have the new result. And then here is the new the result from the t-test. And then what they're gonna do is, we already make this one, and then we want to add this information in the next row. So this R combine means row combine. So before I run, this is from the first proteins. But if I run this, now it has the 2 rows. So, and then just they print I equal 2, and then repeat and repeat and repeat until the last proteins. Okay, so we'll run everything from here to here again. You see, we can see the progress. They are running, yeah, so like the 18, yeah, 22 proteins, 2200, yes. So now this is done. And then now all result have all the information. Let's check the dimension of all result. So now this the all result include all the t-test information across all the proteins. And then each column show their log to 4 changes, t-test, and then p-value columns. Okay. So then next step is, yeah, this the row name actually basically came from what we add at the first, but we can also replace this row column later. this is kind of, yeah, not that much meaningful information here. So the next step is what the Olga mentioned. We can adjust the p-value. This p-value is for each protein, but we have a 3,000, more than 3,000 proteins, and then we can just adjust it. There's a function p-adjust. So we can use this p-adjust, or we can also just check the p-adjust question mark, and then it will show, right? It will show what the p-adjust function doing. So we can give them all the vector for the p-value. Also, we can just choose what kind of method they have. They provide a different method, so you can just choose. Anything you want. But here, commonly we use the Benjamin-Hofberg method. So here I just I just said that I want a Benjamin-Hofberg method for p-value adjustment. So this adjustment p-value, I will add this one in the new column called adjust p-value. So let's see, this is originally what we have. So until the p-value, let's run, right? And then let's come back to the all adjust p-value here. Now we have a new column called adjust p-values. So the last step. So now we are ready to draw the volcano plot. So volcano plot, so we need the x-axis for log to 4 changes, and the y-axis we were gonna use the adjust p-value 1. But here in these cases, commonly of a volcano plot, this is we use the minus log 10 scale for adjust p-value. So that's why we add ggplot2, but x-axis for log 4 changes, but y-axis we want to use the minus log 10 adjust p-value columns. This one is exactly same as what the Kylie present on the day 2, but I will just show a little bit more what actually steps going on. So use the tidyverse one. So from the old data, we want to mutate, means we want to generate a new column called significant. And then what significant column have is this one of these two values. But what is this function is if else, which means if adjust p-value is less than 0.05, if this column is less than 0.05, the significant column have these values. If not, these values. Okay, so let's run this. And then like this. Yeah, it shows pretty much everything, but here we go. So adjust p-value is greater than 0.05. So it's like this value. So the significant column have this information. So, and after they updated all result column, including the significant one, let's draw the ggplot. So here, now, yeah, so now they are ready to draw it. The x-axis is log 2, and then here so it should be this one. And then here, over there, let's overlay the point. But make a color by the significant column. So based on these columns. Right? So here is quite extreme cases. They have only one proteins are significant and the rest of them is not significant. So you can see this is a red and then this is the blue and then still the background like this. Next, what I want to add the horizontal line. Especially we use the p-value, just p-value cutoff of 0.05. So we want to make a cutoff line here, right? So we also use the minus log to log 10. So p-value cutoff itself I just want to change this one. So y-intercept, the y-axis intercept should be cutoff value, and then line type is dot. So let's say here I just run. Now you can see here is the cutoff. Simply you can just change to something else if you want. There's also many options that we can search in it if you want to change, ggplot to change line or line type or something like this. So here you can see line type is different. And then next, I also want a vertical line based on log2/4 changes. Log2/4 changes at -1, I want to add the line. So here, here. So here, the 1 and -1, we can add the dash line. As you probably already aware of, we can also change the color. Something like this, right? And then I also want to change these labels for x-axis, y-axis, and then titles. So let's run. So now we have a title, and then here and here. This expression is quite important. It's not important. It's useful just in case especially for the mass expression. For example, here v1 to 10 is the lower, and then we also want to add some line, or if you want to add some space and so on. So this is the how, just so we can use more accurately. And then I also want to change the background, and here is the how we generate this volcano plot of day2s. Then we have another one. I will just run this one first. Okay, what is the difference is here. We can add the text in the visualization, especially something very important one. So pretty much the same as what we have up there. Only difference is this part. So there's also another function called geom text. It means I want to add the text over there. But which data set we want to use? From all data set, just the p-value is the less than 0 point cases is our data. And then for that specific data, we want to add a label, the protein ID. And then they just, add something only this part. Let's just test. So if I remove this part, you will show labeled all the proteins for each dot, right? And then the next one, so I think if you succeed to volcano plot for your data set, I think we succeed for today. Just in case, so the plot that people are quite interested in is a heat map too. So the day2, there's also a script there, but just in case, so let's try to use the same data set and then try to make it. The difference is volcano plot and heat map. The data structure should be different. So for draw the heat map, we need a wide format, not the long format. So here is what we practice. I think it's early today. From IPRG data, I want to change the format. So here, it's the same code what we practice. Here we go. So now the wide IPRG, each column have a log intensity value for each run, right? And then in the heat map, each cell is represent for each values. So from let's start from the wide IPRG one. And then a little bit tweak we need for the heat map. As I mentioned, the wide IPRG is data frame 1. And then which means, first column have a protein information, which is a character. the second, and then afterward, it will be just a numeric value. But the heat map doesn't like it. So the heat map just want to have only one matrix with everything is a numeric one. So this is the what I do it. So first here I just removed this protein column, which is a character, right? And then after that, I just make this is just matrix type of object. And then T is we just want to change column and row. So now the next the protein will become a column, and then the run will be the rows. So after I run, if I run the CRC, it looks real weird. So I just want to look at first 10 row and then first 10 column. So here we go. This is how it look like. So now, as I mentioned, now each row is for the run, and each column for the protein. But before I just removed the protein name, but we want to know it, right? So here I just add the column name here as the previously the protein information. So let's run this, and then now this data have the protein ID for each column. Just in case, here sum is NA means I want to sum, I want to count if any value inside is NA values. So here they just show yes or no or something, but sum show means there's a one NA value in the matrix. So you can just easily count this. Another line, but actually in the day 2 means, okay, if they have a NA value, the heat map cannot find what color show this specific cell. So we actually need to give them some values. So here I decide to impute this missing value for median median value per that specific protein. So this is also another function called apply, means data set called CRC. The 2 means each column. If any value in that column is missing, just add the median value of that column, right? So if run, it's look like nothing happened. But if you count this one again, now there's no missing value. Then we can draw the heat map. So heat map, and then just, here we go. So now each row is MS run and each column is a protein. Actually, this is more than 3,000 protein there. And, it's, not that much meaningful over there. So just presentation purpose, I just select some important protein, just less than 10 proteins, just to practice a little bit more, right? And then this is what I did, the same thing, just changed the format one, and then let's try to do this one. So here we go. So same thing, but less number of the proteins. So here is how they do it. And then, the clustering is, I just used the default one. So now with this one, you can see this 3, 3, 3, 3 are clustered by each sample, which is quite, what we could expect. And then based on this, the protein, they also make a cluster. So we can have some different clusters and so on. But this is also, we can find more information over there. If you want, you can also practice in the TS section. Here, I know this is we have a base on this row name, but I also want to add their original condition information and add a bar here. So the original information, I think, so up to here and here, everything is just same. Important group information is these samples, right? So I want to get this information. I use this code, it means a subset of the string. I want to get subset of the character from this information, which means each row, I want to start character 13th to 19th. So 1, 2, 3, 4, so 13 to 19, I want to get only this part. So let's run this. And then what we have is now this condition have us only sample 1 to sample 4 information. Then this sample information, I just wanted this one make a different color by the sample. So here is how I add this part. And then here's the same thing, but I just add one more option, which means I want to make a row sidebar for row. For row, I just want to add a sidebar here by these condition colors. So here's the, I can add it, and then you can see how, you know, this is a very clear and an obvious case, but if you have a bigger case, so you can see some patterns. Actually, if you can change a call, C-O-L, you can also add a bar over here. And then also last part is also from the Kylie's one. You can change this color scale. So in the cases, we need some package which already have a good combination of the color, right? So then let's see here. We can just change the color scale like this. So this is the how we can just go through the one comparison for one data set and then draw the one volcano plot. So now I think we can move on to the TA section. Here is the exercise. This is the same plot, same flow. So, but I want everyone just try to do the t-test for different condition, and then adjust your volcano plot as what we want.
There's a couple of questions as well.
Right, how to get the legend of the color condition one. Okay, I will try to find this way and then just put it over there. Yes, he map, yeah, he map legends. You mean this one, right? This, you want to add this color legend over here. Yes, I will try to find a way. Is it possible? Could you share the example of the R code and ANOVA test? Yes, so yes, so we can just replace the t-test part. So I will make some, you know, short script, and then and you know, this is the exercise, and then I will put all the answer for exercise put in our GitHub, so you can find this script as well in our GitHub. So I think I will upload it in the exercise, and then day 3. Now we don't have it, but I will add an answer sheet and then the script for the ANOVA test.
So,
yeah,
sorry, I may have missed. So what would you propose? We have 10 minutes left, so 9 minutes.
Yeah, so officially 10 minutes, but I think just try to use your time over there. And then, yeah.
So maybe we should wrap up the main webinar and use the remaining time with the TAs, right? So
yeah.
That's the plan. Okay, so in this case, let me just make a couple comments for tomorrow as well. So I hope that today you had a chance to see how we can use base R and also intermediate R, like tidyverse and dplyr, and also some of the packages such as heatmap or functions such as heatmap to do different types of analysis at different levels of complexity. And especially if this is new to you, I very much encourage you to spend some time now with the TAs and maybe work on your own. So our plan for tomorrow is to work with more advanced packages which are specifically designed for mass spectrometry-based experiments. So half of the time tomorrow, we will talk about MS Stats, which talks about proteomics experiments, and we'll touch upon the imputation and normalization and things like that. And the other half will be a presentation about Cardinal, which is a R package designed for imaging mass spectrometry. And the interesting aspects there is working with raw files and also working with files which are very large in nature. So to make sure that you benefit from tomorrow's discussion, especially as far as R goes, we very much encourage you that you work through the exercises for today. So with the TAs as much as like the remainder of the time, and maybe on your own as well. And we will post, of course, the video of on YouTube after that. Okay, so I think that's it for the main webinar, but please reach out to your TAs now if you would like to have some clarifications. Meena and I will stay here for the next 10 minutes or so, 5 minutes, in case somebody has questions in the main room as well. And if not, thank you very much, and we will see you tomorrow. So we have 10 people left. So if you have questions to us, don't hesitate. And if not, we will just wrap up for today. Okay, looks like there are no more questions.